Hello everyone, welcome to the April 23rd edition of Math 371. Quick reminder, you have online homework due on Friday. Okay, so today we're going to examine eigenvalues again. And what we talked about a couple weeks ago was that the fundamental theorem of algebra tells us that every polynomial factors into linear terms over the complex numbers. All right. So we're going to use that fact because sometimes, and frequently in fact, we get characteristic polynomials that have complex roots. And they actually lead to a very interesting theory of eigenvectors, eigenvalues. So we call lambda a complex eigenvalue if it is a complex number and there exists a non-zero vector called a complex eigenvector if ax equals lambda x. So one thing I'll note is that we only call it a complex eigenvector. So lambda is equal to a plus bi, and we only call it complex if b is not equal to 0. If b is 0, then it's just a real number. So let's look at a matrix of this form and compute the characteristic polynomial. What are the roots of this polynomial? Well, you probably know that the roots are I and minus I. So this factors, but it only factors over the complex numbers. It does not factor over the real numbers. So let's find the eigenvectors. Well, to find the eigenvectors, I need to subtract off lambda times the identity matrix, and this has i's in it. And now we need to row reduce it. So row reducing over complex numbers might be a little bit of a pain. So it should be a 1, and negative I squared is negative 1. So this should be negative I, and this should reduce to this. So let's kind of see what this is telling us. This is telling us that x minus iy is 0, which tells us x equals iy. So we might pick an eigenvector of I1. So let's check that this is an eigenvector with eigenvalue I. So this is eigenvalue I. And what we get is we have our matrix times I1, negative 1 I. And this is precisely equal to I times I1. Okay, so let's do the other eigenvector. This will be for the eigenvalue negative I. And this becomes 1i, 1i. So this tells us that x plus iy is 0, which is x is negative iy. So such a vector might be 1, negative I for our eigenvector. And let's check. So negative 1 over negative I. So this is negative I times, that's negative I, 1. So some important facts to know are that I times I is negative 1. So I is negative 1 over I. Negative I times negative I is negative 1. So negative I is negative 1 over negative I. All right, so we found the eigenvectors, but they're complex. So let's say we want to ignore complex numbers for a few minutes and see what happens. So we're going to have an example where we let A equal the matrix 0.5, negative 0.6, 0.75, and 1.1. So we know that real eigenvectors and eigenvalues the eigenvectors are scaled by A. But let's see what happens when we have complex eigenvalues. So here, the eigenvalues are 0.8 plus 0.6i and 0.8 minus 0.6i. So let's see what let's let the vector x0 equal 2, 0, and let's see what multiplication by A does. So we're going to let x1 is A times x0, and that's 1, 1.5. x2 is A squared times x0, and this will be negative 0.4, 2.4. x3 will be A cubed times x0, which is roughly negative 1.64, 2.34, and basically we're going to let xk equal A to the k times x0. So let's graph these xk from k equals 0 to 8 and see what it looks like graphically. So the first one is at 2, 0. That will occur right here. The next one's at negative, the next one's at 1, 1.5. That's up here. Let's see, we add some more tick marks. The next one will come at negative 0.4, 2.4. So that's way up here. This is x0, x1, x2. The next one comes at negative 1.64, 2.34. So maybe here. Here's x3. x4 should come about here. x5 will come about here. x6 comes at about here. x7 comes about here, slightly off my drawing, and x8 comes at about, oh, sorry, I think I put x0 in the wrong spot. Yeah, here we go. Here's where x0 should be. And x8 should come somewhere around here. So what do we notice? These points are kind of going in some kind of orbit. And if we plotted hundreds of these points, we would get a shape that looks like this. That's pretty different from what you might expect would happen when you multiply a vector over and over again by this matrix that has complex eigenvalues. Instead of sending out in one direction, like a regular matrix A does to a eigenvector, this just spins it around and around. So that is the interesting part of complex eigenvalues. So I'm going to give you guys a problem to work on your notes. Work on your notes. I want you to find the complex eigenvalues and eigenvectors of the matrix 1, 1, negative 2, 3. All right. So now that you've had a chance to do that, we're going to move on to something slightly different. And this involves the real and imaginary parts of vectors. So the complex conjugate of a complex vector x in Cn is denoted by x bar in Cn. So an example, if my vector x is 1 plus I, 3 minus I, then the conjugate of it is 1 minus I, 3 plus I. You just take whatever is in front of the I and you flip the sign. That's what the complex conjugate is. The real and imaginary parts of a complex vector x are the vectors real part of x and imaginary part of x. So if we use the same vector from before, the real part of x is 1, 3, and the imaginary part of x is negative 1, 1. You might be wondering, why are there no imaginary numbers in the imaginary part? Oh, sorry, it's excuse me. It's 1, negative 1. Well, we notice that 1, 3 plus I times 1, negative 1 is 1 plus I, 3 minus I, which is our original vector x. So that's all the lingo that's involved here. The notation A bar refers to taking the complex conjugate of every element in the matrix A. So for example, if A is 1 minus I, 3I, 2, negative I, A conjugate will look like 1 plus I minus 3I, 2I. The real numbers are not affected. Okay, so comment. If A is an n by n matrix whose entries are real numbers, then when you take the complex conjugate, it doesn't do anything. There's no i's to flip the sign on. So what this tells us is that if I take the conjugate of A times x, it's the conjugate of A times the conjugate of x, which is A times the conjugate of x. So what this is telling us is if lambda is an eigenvalue of A, then the complex conjugate of lambda is an eigenvalue of A. But this is only when A has real entries. So what this tells us is that when A is a matrix with real entries, the eigenvalues always come in complex conjugate pairs. Okay. So let's take a look at a very specific such matrix. So let's find the eigenvalues of the matrix C, which is A, negative B, B, A. So we take the determinant of A, negative B, B, minus lambda 0, 0, lambda. And we get A minus lambda squared plus B squared. And this becomes A squared minus 2A lambda plus lambda squared plus B squared, which is lambda squared minus 2A lambda plus A squared minus B, A squared plus B squared. So we need to use some quadratic formula. This tells us that lambda is 2A plus or minus the square root of negative 2A squared minus 4 times A squared plus B squared. So that's 2A plus or minus the square root of 4A squared minus 4A squared minus 4B squared over 2, which is 2A plus or minus the square root of negative 4B squared over 2, which is 2A plus or minus 2BI over 2, which is A plus or minus BI. So those are the complex eigenvalues of that matrix C, and the number R is what we call the modulus of lambda, is the square root of A squared plus B squared. So it's easy to check that the matrix C is this matrix times this matrix. You can just multiply it out and see pretty easily. And we noticed something about this right-hand matrix. What's A over R squared plus B over R squared? Well, that's A squared over R squared plus B squared over R squared. That equals 1. What matrix have you seen like this before? I want you to think about that for a couple minutes and see, where have you seen a matrix where you have these values and A squared plus B squared is 1? There's something this should remind you of. And to remind you of trig functions. It's actually the rotation by phi. So what this is telling us is that our matrix C is equal to this scaling part times some rotational part. So let's take a look at the complex number. If this is the imaginary axis and this is the real axis, and we have our complex number, A plus BI. This is A and this is B. This is R. This is the angle theta that appears in that rotational matrix. And we call phi the argument of lambda equals a plus bi. So what is this telling us? What's the takeaway? The takeaway is that sending the vector x to c times x is a rotation by phi followed by a scaling by the absolute value or the modulus of lambda. So multiplying by this particular matrix with complex eigenvalues can be viewed as a rotation followed by a scaling. So let me draw a picture to show you this again. So multiplication by C looks like this. If I have a vector x, then to get ax, I first rotate by phi, and that comes down to here. And then I scale by lambda. Lambda could be less than 1. So that's what multiplying by this particular matrix with complex eigenvalues does. It's a rotation followed by a scaling. And I claim that every 2x2 matrix with complex eigenvalues can be put in this form after you change the basis. So how do we do that? Well, here's our theorem, whose proof we will omit. Let A be a 2x2 real matrix with complex eigenvalue. Lambda is A minus bi, where b is not 0. And it has associated eigenvector v. What this tells us is that A is P times C times P inverse, where P is equal to the real part of our complex vector, the imaginary part of our complex vector, and C looks like this. So I'm going to omit the proof. I'm going to see if you can do an example without me guiding you too much. I want you to find invertible matrix P and a matrix C of the form A negative B, BA, such that A is PC, P inverse. So we're going to let A equal 1, negative 2, 1, 3. So I want you to go through the steps that theorem prescribes to find the matrices P and C so that A is P times C times P inverse, which basically tells you that A is similar to a matrix of the form A negative B, BA, which tells us that if we pick our basis right, the matrix A operates by rotation and then scaling.